What if the Big Bang wasn't a beginning, but a reflection? I mean, really think about that for a second. What if our entire universe is just one half of a perfectly symmetric whole, and that on the other side of time, there's a cosmic twin made of antimatter, contracting as we expand? It is an absolutely mind-bending idea, and you know what? It might just solve some of the biggest puzzles in all of physics.
So, in this explainer, we're going to go on a little journey. We'll kick things off with the deep mysteries of our cosmos, then explore a fundamental symmetry of nature that could be the key to everything. We'll see how this one radical idea offers a single, clean solution to three different massive problems. Then, we'll put it in the ring against the reigning champion of cosmology, cosmic inflation, and see what a trio of billion-dollar experiments has to say about who's right. And finally, we'll see how it all could come together in a truly grand unification.
All right, so to really get why a theory as wild as a mirror universe is even on the table, we first need to look at the major cracks in our current understanding of the cosmos. These are the big ones, the puzzles that are literally keeping physicists up at night.
First up, the problem of our own existence. See, the Big Bang should have produced equal amounts of matter and its evil twin, antimatter. Now, when those two meet, they annihilate each other in a flash of pure energy. So, by all rights, our universe should be a boring sea of light, with no galaxies, no stars, and definitely no us. And yet, here we are. So, where on Earth did all the antimatter go? Okay, next up is the mystery of the universe's invisible skeleton. About 85%, that's a huge number. 85% of all the mass in the cosmos is something we call dark matter. We know it's there, we can see its gravity bending starlight and literally holding galaxies together so they don't fly apart. The problem? Our standard model of particle physics, our complete rulebook for every known particle and force, has absolutely no candidate for what this stuff could be. It's a total blank. And finally, our universe is just, well, it's too perfect. It's incredibly uniform in temperature in every direction we look, even between regions that were never close enough to have ever exchanged heat. And it's spatially flat to an almost impossible degree. Any tiny deviation from perfect flatness at the very beginning would have been magnified over billions of years into a crazy shape. It just seems impossibly fine-tuned. So we have these three huge disconnected problems, right? But what if the solution to all of them lies in a single fundamental principle of physics, a symmetry that's considered the most unbreakable law in all of nature? This law is built from three pretty simple transformations. First, you've got charge conjugation, or C. That just swaps a particle for its antiparticle. Easy enough. Second is parity, or P, which is basically like looking in a mirror. It flips left and right. And third, time reversal, or T, which does exactly what it sounds like. It runs the movie of physics backward.
Now, here's the crucial point. While nature can sometimes break the rules for C or for P or even for both of them together, the CPT theorem says that the combination of all three is an absolute, inviolable symmetry. You can bend the individual rules, but you absolutely cannot break the CPT law. It's the bedrock.
This leads to the theory's radical core idea. So what if this unbreakable symmetry doesn't just apply to tiny particle interactions, but to the entire cosmos? This model proposes the Big Bang was a CPT mirror. On our side, for time greater than zero, we have our familiar expanding matter-dominated universe. But on the other side, for time less than zero, there's a contracting antimatter-dominated anti-universe where time, at least from our point of view, runs backward. Now, the real power of this idea is something physicists just love. They call it theoretical economy. Instead of needing three separate kind of clunky fixes for our three big problems, this single principle, that the universe as a whole respects CPT symmetry, provides one elegant, built-in solution for all of them. And this just lays it out so clearly. That missing antimatter, it's not missing at all. It's just over there in the anti-universe. Problem solved. Dark matter? Oh, that's not some exotic new particle we have to invent. It's a specific type of neutrino that other theories already suggested should exist. And the universe's flatness? It isn't flat because of some weird hyperexpansion. It's flat because that's simply the most statistically probable highest entropy state for a CPT symmetric cosmos to be in. One idea, three solutions. Boom. Okay, so this brings us to a direct conflict, a real showdown. The mainstream solution to that flatness problem is a theory called cosmic inflation, this idea of a period of insane exponential expansion right before the Big Bang.
But the mirror universe model offers a completely different explanation. It's setting up a testable, scientific battle for the origin of our universe.
And here's where it gets real. Cosmic inflation, by its very nature, would have violently shaken the fabric of space-time, creating a faint background of gravitational waves that we should still be able to detect today. The mirror universe model, on the other hand, produces no such waves. None. The two theories make a clean, opposite, and totally falsifiable prediction. One says this signal, which we call R, must be greater than 0. The other says it must be exactly 0. One of them has to be wrong. There's no middle ground.
So this isn't just philosophy, right? This is testable science. How does this radical idea actually stack up against real-world data? Well, let's check out the scorecard from 3 key experiments with the very latest results as of 2025. First up, we've got a very specific and, honestly, a very fragile prediction. For all the math in this model to work out, it requires that the lightest of the 3 known types of neutrinos has a mass of exactly 0. Not small, 0. The Katrin experiment in Germany is basically the world's most sensitive scale for neutrinos, and its latest 2025 results show the neutrino's mass has to be less than 0.45 electron volts. Now, that is perfectly consistent with the theory's prediction of 0, so the theory survives, but it's tense. I mean, really tense. If the next generation of experiments measures any non-zero mass for that lightest neutrino, the entire mirror universe model is instantly toast. The second prediction is all about the fundamental nature of the neutrino itself. The model requires that neutrinos have to be what are called Maggiara particles, which is this bizarre state where the particle and its antiparticle are literally one and the same thing. Now, the only way to prove this is to spot an incredibly rare type of nuclear decay that's only possible if neutrinos are Myrojona. The LEGEND experiment is hunting for exactly this signal, and as of 2025, they haven't seen it yet, so this means the theory is safe for now, but it's still unconfirmed. If they do see this decay in the future, it would be a massive, massive piece of evidence in the model's favor. And that brings us back to the big one, the showdown with inflation. The mirror universe model predicts there should be a complete absence of those primordial gravitational waves in the afterglow of the Big Bang, what we call the cosmic microwave background. And here's the most powerful and kind of paradoxical piece of evidence. The BICEP/Keck experiment at the South Pole has been hunting for this signal for years, and as of 2025, they have found nothing, not a peep. Every new dataset is more sensitive, and every single time, the result is consistent with 0. So, the persistent failure to find the smoking gun of inflation is, in fact, the strongest experimental evidence we have for the mirror universe. And this brings us to what might just be the most profound implication of this entire idea. It takes what we thought were totally separate fields of physics and binds their fates together. I mean, before this theory, these 3 experimental quests were seen as completely separate. A neutrino physicist working at Katrin didn't think their work had anything to do with a cosmologist at BICEP looking at the dawn of time. But the mirror universe model says, hold on, you're not in separate fields at all. It claims the answers to all 3 of these questions are deeply, fundamentally linked together. As the source material puts it so well, the BFT model transforms these 3 independent, billion-dollar experimental pillars into the load-bearing elements of a single, unified, and eminently falsifiable structure. What that means is a definitive result from the gravitational wave search wouldn't just tell us about inflation, it would tell us something fundamental about neutrinos. And a result from the neutrino experiments could tell us about the first moments of the universe. It's an all-or-nothing game. And so, that's where we are, left with this absolutely tantalizing possibility that these 3 separate lines of inquiry, probing the tiniest particles and the largest structures in the cosmos, might just be converging on a single, astonishing truth, that we are living in a universe that has a perfect reflection in the mirror of time.